The presentation that I'm going to talk a little bit about, unfortunately, it doesn't have to do with the prediction of cosmological movement. It doesn't have to do with weather. We're looking at the complexity that's more of a finite nature that we deal with in the automotive industry. Great. Very good, thanks. So just as Shiloh is a company, we're organized around helping to transform transportation in such a way that we're being more sustainable to our environment. And because we're a little bit short on time, I'm going to be flying through some of the slides and not talking about everything I plan to talk to. So in any case, our mission is designed around lightweighting of all kinds of bits of the transportation puzzle. We work on various pieces of automobiles, powertrain, body structures, and chassis, and all, by and large, that proposition is about reducing weight, complexity, emissions, overall cost, and fuel consumption. As an organization, we work in a variety of different materials. So one of the things about Shiloh is we like to think we're material agnostic. So we really don't care what the material is. It's a matter of finding the right material for the application. And that's very telling because that's exactly what's needed in the industry now as we're mixing more things together to come with integrated structures that are going to be that are going to help us lightweight, reduce emissions, and so forth. So closures, driveline suspension, engine transmission, propulsion systems, we make parts for all of these bits of the automotive puzzle. We're in all three continents, three major continents, in the US, in Europe, and in China. So we're offering these kind of similar solutions globally. And that's of interest to the OEMs because they're looking for the ability to, if we're launching a project in a location, they would love to be able, if they're launching similar projects because they're making platform identities more similar, be able to launch it with the same company in various places because it reduces their overall launch cost. So we're all over the world. We're about $1 billion in sales, a little bit over as of, as the 2016. We figure we'll be about the same this year. And we're doing organic growing and growing with acquisition. Well, we all know about our transportation world. We have a lot of density problems. We have emission problems. We know that there are lots of trends. We are looking to drive emissions down. We're looking to drive miles per gallon up. And one of the ways to do that is to make sure that the vehicle frames are as light as they can possibly be. So that's one of the things that we work on. So we're on this vehicle platform. We're in a new engineering moment. The OEMs are expecting more from the components using less material. So it's about lightweight, stiff, ductile, strong, less over-design, and with consistency in the whole range of production. So if I'm making 1,000 parts per day, all 1,000 parts are going to be in that capability range for the properties that they expect. Because we're talking about replacing bits of the automotive puzzle that people's lives depend on. So it's extremely important that the consistency of the process, just like it is with chips, just like it is with medicine, it's the same with these components that make up the frames of vehicles. So we need narrow capability bands in terms of our processing, and as important as anything else, they want to buy structural components and they want to buy them like they're regular commodities. Nothing special, just perfectly executed every time. So the areas where lightweighting is important is we have it in all four of the domains, and there are new materials that are coming out and new processing that allow us to be able to do some changing, to be able to change this engineering conversation on every one of these component areas. A lot of parts are considered. Steels are still a primary focus in vehicles. They're inexpensive. There's a lot of good analysis behind them. They're very predictable. Aluminum, magnesium, both sheet and castings are some of the things that are emerging into the market, as well as carbon fiber, plastics, and other emerging composites. So this is all the things that are changing. We know that the framing of body in white and panels, so body in white is that bit of the puzzle of building the vehicle. That's before the doors are added, before the wheels and suspension are added, all the closures, the seats. It's just before they dip it in the white paint before it comes up. So that's the structure of the vehicle is what we're looking at as this body in white. So these areas are really are traditionally steel, but in the process of driving this lightweight conversation are moving more and more into other materials. So one of the things that's an advantage is the simulation in the CAE for steel is very well developed. It's got a lot of history. These are components that are on the shelf in every one of the OEMs. They can take it down and say, okay, I'm going to use this steel for this application. I know how it's going to respond over the whole life of that particular design. So it's very low risk. So there's got to be some compelling reason, and by compelling, it means compelling and then validated with data, strong reason to make a change. So you have people pushing, but at the same time you have engineering resisting, because engineers are typically conservative and they want to make sure that the integrity of the product remains at a very high level. So if we look at typical vehicle construction, you've got this area of the safety cab, which tends to, you design around being very, very strong and stiff. And then you have the areas in the front and the back, which are opportunities for lighter materials, provided that you can actually count on the homogeneous structure. And that's one of the things that is the next step here. So I'm kind of building a case as to why we're interested in the computing that comes from having big machines and big core running a lot of nodes and analysis on the things that we're doing every day. So this is the current design thinking. Mercedes looking at the same thing, and this is across the board. This is the way people are thinking. So you've got new requirements, focused growth, but you need to have this consistent homogeneous structure in the load paths. And especially where we've got frames, we've got crash relevant strength, generating lighter vehicles. That means the vehicle's lighter. You have to migrate to other concepts to reduce the mass. And whereas automotive is starting, it's going to follow all the rest of the vehicle structures and a lot of other white goods and so forth to be able to do lightweighting, using less of the material with greater properties every time. So if we look at the process of one of the casting processes that we're engaged in, which is this high pressure die casting puzzle, in Europe and a lot of the European vehicles, and starting in the US, there are a lot of these places where these structural members are being introduced into the framing of the vehicle. And as you can see in this particular Mercedes vehicle, you got a 20 kg reduction in weight. So that's a big incentive to be able to take both the weight out and the cost out in these particular areas of the vehicle. There's a lot of other vehicles that show up as being places in that frame where lightweighted structures end up being an opportunity. And if we're looking at the casting, there's the older casting methods which are gravity fed, which obviously are a lot simpler to model because they're moving at a very slow fill rate, and you can model a lot more simply. But the area that offers the greatest opportunity is this high pressure side, which has the greatest challenges on the modeling. So we talk about the high pressure has a fill speed that's very fast rather than a calm progressive fill. It has violent splash parameters on the inside of the die. It's got bounce, it's got entrapment, and that's an area where a lot of the casting optimizing and lightweighting is having a big impact. So you've got fine details, might be a millimeter and a half or 2 millimeters or 2.5 millimeter wall sections. They're big castings, filling out over big areas. You've got very fast solidification. The dendrites are in the 7 to 12 micron spacing. It's got good properties without having to heat treat it. These are some of the advantages of being able to go with this very fast fill method. And you can even enhance it with heat treating if you're doing the right things on your casting process. So one of the things that was looked at earlier was the dendritic size as a predictor of what the mechanical properties are for a particular shape. So if you start looking at what would be the other casting methods, we have dendritic spacing that's maybe up between, let's say, 50 and 100 microns. And it would, to get the necessary properties, you would have to heat treat them. If you look at some of the casting, the high pressure casting methods, we've got dendritic spacing that's down in the 10 or 12 normally, and with stuff that we're doing with some of the new technology, we're down to 6 to 9 microns in the spacing between dendrites. So that ends up being a very, very good predictor of high properties, and that's one of the things we need if we're going to put these in a structural application in a vehicle. So if you consider the modeling case, we've got this metal velocity that's moving. Maybe it's got a 15 or a 20% fraction solid, so the viscosity is something you can predict within a range. It's typically pressured through a 3 millimeter gate, so you have a kind of atomization spray at this maybe between 15 and 2,500 inches per second. Fill speed. Complex structures, very small radius, so you can imagine the modeling challenge of having 2 millimeter, 3 millimeter radiuses and corners and trying to see how that structure is going to fill. You have thick sections and thin sections, and they moderate over the part. You have a fill window that's 20 or 60 milliseconds in that range. So if we think about that violent feed, it's filled, it's done. It's already over, and we're having to predict the way that could be 20 pounds or 30 pounds of materials moving through the die in that 20 milliseconds. That's part of why the HPC is important to us. And then, if we can model the cooling effectively, we can reduce the dendritic structure even smaller, because the dendrites are a function of cooling speed. And we end up getting 10 or 15% greater properties in the same kind of geometric shapes. So if you put the hat on of the engineer saying, okay, how am I going to get more properties out of less material? This is the path that I need to be taking. So one of the things about castings is typically they were always over-designed because you couldn't end up predicting a homogeneous structure. So you would end up saying that if I were designing around 150 megapascals for a particular kind of Goodman curve yield on the life of a component, I might design around 70 if I have thick walls. So it was a kind of over-designing, which is very costly, and it's not something that the engineers are looking at continuing to support. So the only way to be able to have this be able to reduce the over-design is to really have a continuous homogeneous structure on the inside of a casting wall, which is solidifying, has to solidify quickly, it has to solidify the same way, and it has to be free of gas. And those were all problems that were part of the high-pressure die-cast solutions. So we do all that right, and then we lightweight by reducing the mass of those typically loaded castings through the design and what we can do with our design areas. So this is kind of the challenge. You have this fast fill, you have streams of metal that need to flow together, and they need to knit and intermingle, and it's all happening in this 20 or 30 millisecond time window. So one of the things that you typically have with a typical die casting is you have a skin which solidifies very quick, and then you have a core which is typically full of gas. Now, you have metal pressure Boyle's law will take those bubbles and turn them so they're invisible based on the amount of metal pressure you're bringing to bear. But if you try to heat treat the part, they all blow up again and you end up with a discontinuous material. The other thing about typical castings is you would have a different dendritic structure. You might be double the dendritic size in the thicker core than you are at the skin. So One of the things about these new structural parts is they're almost all skin. When we're talking 3 millimeters, you've got a skin on each side and almost nothing that's core on the inside. So you have, if you're managing the properties of the raw material effectively, you have the possibility, and it's something that's proven in the parts we're making today, that you can make these structures very, very homogeneous and such that they can be predictively analyzed in the computer models that exist today. But the main thing is that you need to be able to do the modeling effectively. So it used to be they would do, you'd have shell modeling. So I would have something for the skin on both sides, and I'd do something different in terms of my mesh on the inside for the web. And that was, I could put lesser properties in the web, and I could make the skin tighter, and I could end up with an analysis. The trending now is to make it all the same with small mesh, which means that the computing power has got to be that much greater and the analysis time is longer. So that's what we contend with, that's what we need from the industry. The other thing is that we need to be able to predict, because if we're feeding in one area of the part, we'll end up with different differential properties on one side or the other just based on the cooling gradient between those two areas of the steel. So cooling, and I'm bringing it up again because this is what Adrian's going to talk about in his part of the presentation, that we need to model better. The cooling is critical for us to be able to continue to make these homogeneous structures as good as they can possibly be. So, of course, it's not just dendrites. You've got to be free of oxide. You've got to be free of impurities. You've got to have all the pieces of the puzzle perfect. Otherwise, you can have a good structure that is poisoned by bad practices. So the two things go hand in hand. Your practices have to match a really, really tight control of your process capability. So typically, we're doing all these different kinds of analysis. These are all things you've seen. We typically, we're using Magma, we're using Flow3D. We use them differently based on the complexity of the parts. If, for example, I'll just run one of these. This is an IP structure. So typically this would be the tooling we would use. That happens to be a Flow3D simulation. I have a Magma over here as well. This is the kind of clarity and the kind of definition we need to be able to predict how the streams are going to flow together, how the metal is going to knit, and the properties ultimately that casting is going to see. This is kind of what we like to see. This is a shock tower that is used on GM. You can see that you've got smooth flows, everything's running together, and it's over the part into those overflow sections. Another thing that's interesting is we need to predict, and this is another cooling factor, you need to predict the areas here as solidification's happening that would end up being puddles of hot mass in the middle of cold sections, because that's what will generate shrink voids, which then reduce the mechanical properties of that geometry that you're casting. So these are the things that our cooling simulations generate for us, that allow us to put additional cooling in those particular areas that would normally generate a trapped flow. So as you can see, we're looking at dies which have huge numbers of water lines or hot oil lines generating the cooling passages in and out of the castings. We end up with modeling the cooling. So the cooling is looking at how is it solidifying. So these are all things that we model to make sure that we are going to be able to make a good dense casting. As you can see, the more complicated the part, we end up with a lot of different structures that we're working around. We end up doing iterations, and we don't want to iterate these in steel. We want to iterate these in a computer where it's inexpensive relative to doing this with a $500,000 die. I can't cut this up and continue to put different cooling passages because I didn't figure it out very well the first time. I got to have first pass success. And this is what we do to end up generating those kind of results. So this was the challenge, and this is why we had Oak Ridge help us with this in this collaboration. And Adrian's going to come up and talk about what some of the findings and what the process is looking like. Cooling prediction is critical for solidification control. Where the multi-physics of this and the microchannel cooling, we need lots of computing power. As you can see, the CPUs we have inside of Shiloh are too small to be able to manage this. They work a lot of our other simulations. Maybe it takes a day, maybe it takes 2 days, depending on how complex and how many nodes we're fussing with on the model. But we needed more. So we set up this concept called microchannel cooling, testing boiling models, some heat transfer stuff, and assessment of the model for microchannel and validating the transfer coefficients and identifying the configurations to make the most sense. So from here, Adrian is going to come up and talk about what some of the results were, and then I've got a couple slides at the end just to kind of conclude.
Good afternoon, ladies and gentlemen. I'm Adrian Sabot. I work at the Oak Ridge National Laboratory. It's a pleasure to be here and illustrate some of the challenges that we faced in this interesting project with the Shiloh. So high pressure die casting, it's a very interesting process, and I took the liberty and digitized some experimental data that were presented in a paper. And you can see here the heat flux that's actually measured in situ. You get up to about almost 10 megawatts per meter square. That's really a very high heat flux, but that lasts only a short while. The die is closed, the material solidifies, is kind of cartoon represented there by red coloring. Then you open the die up, you take the part out, and you have additional cooling of the die using lubricant. During this very high heat flux, the die itself experiences some very high swings in temperatures. In this particular example, the die temperature actually was measured with a pedometer, and the cutoff for that pedometer is 350. So actually the swings in temperatures are about from 200 up to almost 600, and that happens with every shot. And you can see here different parts of the process from, when the die is closed, when the casting is, when the billet is injected, then you have the die opens, and the casting has to solidify within that 20 seconds time frame. So how are we going to cool that die? And this is a CAD file that I took a snapshot that was provided to us by Shiloh. And you can see here different cooling passages, and these are some of the new cooling passages proposed. I took the liberty of coming up with this table. You can see in the first line here, what's the state of the art, meaning involving large cooling channels, of a tubular shape with a single phase, meaning liquid, cooling, which is slow, and that yields, basically longer cycles. So Shiloh proposed to use mini channels, and they can come in different shapes, from being flat or annular in geometry. And the benefit here is brought by two-phase cooling. You have basically boiling of your coolant, and that basically provides an increased heat transfer coefficient by about 5 to 15 times, resulting in shorter cycles and better properties. The challenge that we faced with is that there are not really any correlations available in the literature to prescribe how is this flat channel or this inclined channel is going to cool, And this is just one die insert here pictured, cooling of a die insert. The die is actually, let's say, 10 times larger than this little image. Again, the challenge is that the only correlations available in the literature are those for, round tubes and, that are used for boiling, simulations. So we set up to analyze some of these configurations, and actually we looked at some of the flat channels in this work. How's the project proceeding, I guess? So Shiloh came with a very nice concept, and it was matched up with our expertise in metal casting, computational fluid dynamics, two-phase experience from, let's say, nuclear reactor and fusion energy, and of course, high-performance computing. So we're going to analyze, we're going to look in detail of two-phase cooling for these unique geometries, and we're going to provide a database that can be used in, later on in large-scale simulations for the process itself. This is just a small cartoon illustrating the data exchange between the team. And I just want to illustrate that the water boiling, I guess, it depends on the pressure of the coolant. We'll take that into account. So again, we took up, we came up with a simplified configurations that we can take a look at it. And this is our geometry that has, quite a few factors here. So if you look at the main design variables are what I called the die thickness here on top of the cooling channel. Green is cooling channel. This is die to cooling channel distance. B is going to be the width of the thickness of the cooling channel. Then you have a certain mass flux of the water, of the coolant. So guess what? You have to mesh, that channel very nicely because, we know from turbulent simulations you have to have very nice defined mesh nearby the walls. But that's not the whole story. The whole thing looks like this. So, it's, and this is, by the way, this is just a third of the mesh. It's actually longer, but I wouldn't have time, I wouldn't have real estate here to put everything on one single page. But that's not the whole story. We spoke about using, about our design variables, and we're trying to see which some of these design variables are actually going to produce some valid configurations that can be used in practice. If you think through the cases here, you can consider 4 cases for A. I guess I didn't put the units here. Millimeters, and this is kilograms per meter square seconds. And the other aspect of it is going to be the inclination of the entire cooling channel. You have more than 1,000 possible configurations here. So high performance is not only needed. I'm going to go back, if I can, to the mesh size, which is not a small mesh either, but also from the number of cases that we simulate. What we're looking for, we're looking for the optimum. If you ran with the low mass fluxes, you will have boiling, but your temperature will go through the roof. If you have very high flow rates, you're not going to have an efficient cooling because you're going to be confined to the liquid. So I guess the optimum is somewhere in the middle. Some of the results that we got, so I guess I'll try to be as specific as I can. For a 9 millimeter thickness, that's a die right here on top of the cooling channel. The molten metal will be up on the top surface, and the molten metal is not simulated. Instead, we impose that heat flux that I showed on the first page. So we remove that heat flux, and we're trying to see basically what flow rate do we need for the coolant to keep the die temperature under some acceptable numbers. So you see, this is before cycle onset. We simulate a couple of cycles in order to make sure that we reach steady state. And just want to mention here that we also take a look at the amount of vapor that's generated in that cooling channel. Sometimes we don't have any vapor. We discard that case. Sometimes, we have too much of it. And in this particular case, we found out at low, small mass fluxes that even before a new cycle will start, the top die right there is actually insulated by a thin layer of vapor. So it stays there, it doesn't get removed at all. So when the new cycle starts, no wonder that temperatures are going through a roof. We have about 790 here. For another configuration that we look at it, so again, here we have a smaller die-to-coolant thickness right here. If you can take a look at these temperatures, we came down from 790, I guess, to about 500. The die can reach up to 600. So it's a very acceptable number. Let's look now at, in this particular case, the last case. Again, color-coded blue is no vapors, light blue, some certain fraction of vapors. The units here from 0 to 1. If you have 1, you have everything is vapor. So initially, there's no vapors because it turns out that the fluid has actually carried out that top layer. You see how does it form? So it's interesting. It proceeds like that. You have a liquid layer confined on vapor layer confined on the top of the channel, and gets convected away as the cycle proceeds. And this is a very good example. That's what we would like to see in our designs. So we identified at least one design that is going to work. So more data here. If we look at the die surface temperature, we identify that this parameter right here, we call it A, die-to-thickness, die-to-coolant thickness, is very important because you can overheat the die, if in cases where this dimension is too thick. So the take-home point here is not only that the cooling is important. It's important where is that surface placed. Is it going to be up close to the die, or is it going to be away? We know that if it's going to be away from the surface, it's not going to be efficient. And this is the exit vapor fraction. We learned something else here too, from that previous page too. Instead of looking only at the exit void fraction, you're looking how much boiling we get. That's an indication for us when we conduct these 1,000+ simulations that we have. We're trained to phase cooling, which is very efficient. We have this rocky behavior, and it's more important also to take a look at how much you have, how much boiling you got, I guess, how much vapor in the entire cooling channel. Pressure affects boiling. So here it's pressure at almost room temperature. We took the extreme case. And we can see that there is some variation in the die surface for slight variation, I guess, in the die surface for the 41 psi. And some of the temperatures are slightly, different in the cooling channels. And again, we spoke about the inclination of the cooling channel. I'd like to emphasize that all the data in the literature is limited to the vertical and horizontal. There's not much on the inclined. But sometimes we have to use inclined surfaces too. And or actually, in this case, not only have the coolant, from the bottom, but we said that for the upper die, we have to do it injected from the top. So we got one example in which we actually found that for this configuration, the die overheats, exceeds far away, our threshold of 600 degrees Celsius. And if we incline that channel, for the same flow rate, nothing happened, nothing else was varied, you get reasonable temperatures. So the inclination is definitely has to be taken into account. And you can see here again that insulating vapor layer, so I guess the horizontal channels are the least desirable, in this case. While again, we have evidence that between cycles, that vapor layer, the insulating vapor layer, is actually, convected away very nicely. And again, so you have boiling, no boiling, boiling, no boiling. The cycle goes up and down. Finally, what we like to do, and we just set up, we're going to use the optimizer in the Star CCM Plus, and this is just a few cases that we ran. So this is our design experiments, and we set out our template to monitor some of the criteria, and we're going to screen some of these designs automatically, and then we can find out, again, this is provided from that simulation that we ran. What you see here is kind of a sensitivity analysis. What this tells you is that, for example, if I'm looking at the, this is the effect of that die, coolant to die thickness. So the higher the number from 0 to 1, the more sensitive, that variable that we're going to follow is going to be. So identify that this is very critical, Turns out that the dimension of the cooling channel is not that important. Interesting. I guess this slide concludes my talk, and we're halfway through the project. We have a lot to cover, but I think we have a great start. Thanks to the great collaboration from Shiloh.
The one thing to mention here is that what you're seeing here is a piece of the steel section that maybe the weight of the steel is maybe about 6 kilograms, and it's an insert sitting into the die. So partly the next thing I was just going to mention was it's why do we care? So we're doing all this analysis. We're looking at how the cooling is going to affect the various channels and kind of optimizing this case. So if we can, there's the simple facts that if we're too hot or too cold, the die life is vastly reduced. So that means cost to customer is extremely high. So let's say it was a typical die with a primary material which is kind of abrasive on steel to start with because it's got low iron content because you're trying to optimize properties. Maybe you have 100,000 cycles. So if you have a cavity that's rather expensive, that means you're replacing that cavity every 100,000 cycles. Now, if I can get 15 or 20% greater life out of that same cavity set, which I can do if I'm optimizing the cooling, cost to the customer goes down. So that's one element. Another element is just the resources used that are reduced, and that's everywhere. That's the heating of the metal, it's the casting, it's the taking the die out, it's changing everything. It's all that wasted effort, which is not something that it's waste that we need to eliminate. It's not something that's no value add to the customer, so it's useless, wasted time. But the most important thing is when we're taking these castings and putting them in structural applications, the thing that's critical is that a normal aluminum casting maybe has an elongation of maybe 1% or 2%. So that means it's going to come up to it's going to go through its elastic deformation, it's going to come up into the plastic zone, and it's going to move from plastic to failure very quickly. It's going to shatter. So if I'm looking at a frame of a vehicle, I don't want to have the frame shatter. I want to be able to design the collapse and the absorption of the energy of that component as let's say the event is taking place, whether it's a half frontal crash, whether it's a side, whether it's a rollover, whatever it is. I want to be able to design the collapse of the components. With doing some of these changes that we typically do, we're ending up with elongation that's in 13–14% range. So I'm comparable with what I'm doing with steel with properties that are good. So The benefits, improved die life, better mechanical properties. There's, the obvious reduction factors, less machining. The other thing is cycle time reduction. What Adrian showed was there was this, you looked at the cooling going through the line where I had steam formation at the wall of the cooling channel, and then it began, and then as it cooled off, it moved out of the way. So one of the things that's looking at is when I make the casting, I have about maybe 15, 16, 17 seconds where that casting is sitting in the die, solidifying. And that's what makes the dendritic structure. So that's what makes everything tight. That's what makes the properties greater. And if I can optimize the cooling, I'm picking up that 20% or 15% on my mechanical properties without sacrificing a thing. And in fact, with making the process more efficient. So it's very important for us to make sure we're managing this cooling activity very carefully. So the other thing is, I mentioned before, we got these complex dies, you want to validate them electronically. You don't want to validate them by making the steel and then remaking the steel because you figured something wrong. The other thing is we've got to have these metal flows predicted very well. And in this 30 millisecond window, I need to make sure that metal is binding together with the right kind of properties. So I just figured I would throw in a few examples of where these are being used. So this is a cross-car beam, the IP panel reinforcement, in the vehicle, and we do this in magnesium. So magnesium is even more complicated because the solidification is even faster, and it doesn't flow together very well. So the simulation has to be that much better because I'm filling in maybe 30 milliseconds, not even 40 or 50. We also do shock towers that sit on as you can see in the vehicles, various kinds of subframes, rear rails that would go over the rear wheel. And all of these are crash components that need to have elongation and properties you can rely on. So here's an example. So if you go from what was the old construction to the new construction, I've got a 10-pound weight savings per vehicle. I've got a 50% reduction in machining content. And I've got a one-piece casting which allows for kind of an elegant dissipation of force, and you can manage the way the collapse will take place inside the vehicle in a very, very effective way. The other thing we do is I can take and put a heavily loaded aluminum casting in a rear axle that I couldn't do before. That would normally be gray iron, but if I can drive properties up, I end up with a solution it's a 44-pound weight reduction per vehicle. Significant. It's a big deal. So, conclusion. We need to engineer to optimize the best material and processing to support the innovative things that customers are doing in the transportation system. We have the properties and the mass of our structures, we have to look at them carefully so it's multi-material, right material in the right spot. We need to do improve our simulation analysis results so it correlates perfectly. We have to use our results to make the most consistent in this kind of narrow capability range. And then, speed, of course, we all want to do it faster. We want to be able to do it fewer times. Typically, we could do 10, 15, 20 simulations to make sure we're honing down. So if I look at every one of those, it could be a day. I have a lot of time that if I could do faster, it would be much better. And finally, you've got to partner with the right people. Whether it's people in the steel, whether it's analysis, resources, you got to partner with the right people to make sure this is coming together that you can validate well. Because ultimately, the customers are only interested in technologies that they can validate electronically before they risk anything. Now, it's very unusual that Ford in the pickup truck decided I'm going to go with this all aluminum frame. This was a huge radical shift for them. So it's very impressive, very, very gutsy. and it paid off. But this is the way the industry is going in North America. Europe is already there, and China is actually going to be kind of going very fast. So, thank you.